Okay, good morning. Section 7.8, improper integrals. We are going to wrap up chapter 7. Let me share this with you. Here it is. We'll share this with you. So here is sort of the calendar. I'm thinking that per sort of the school's direction, we don't want to have a test until next week. So we're going to have this next week sometime, most likely toward the beginning, although it doesn't matter. We can get some feedback from you, but we are going to go on to chapter 11. In fact, we're going to go on to chapter 11 this week. So on the calendar, I spread this out a little bit more. What I would like for you to do is, if you didn't give me your quiz, then make sure you get your quiz to me today so that we can learn how to submit things and grade them and get them back to you. We're going to do improper integrals today, and then I would think that we'll do maybe section 11.1 and maybe even 11.2 this week. Okay, 11.1 for sure. And so then the following week sometime we'll continue with chapter 11 and we'll do the chapter 7 test. We're going to do 11. I'm thinking that if we can finish 11 off, we're done with the class. Okay, so we've got 5 weeks left and 15 days. I think there's 12 sections. It's still going to be a bit of a push, but I think we can make it. Okay, it's going to be chapter 11 is our last chapter, so we're on the home stretch now. Okay, you ready to do this? Improper integrals. There are 2 types. Improper integrals are going to handle a case where we have an infinite discontinuity sort of in the middle of the integral. And so a point discontinuity, no problem. Integrate right across the point. But an infinite discontinuity, our region's going to be unbounded. And then we saw the other day that sometimes it converges, sometimes it doesn't. And so there are 2 types. There's the kind where we're going, where x is getting bigger and bigger or smaller and smaller, and it's not bounded. Okay, so those kind look something like this. We've got, this is type 1. Type 1, right? Which is an integral that looks something like this. We're going to start somewhere. We're going to go to infinity. And we're going to say, all right, how do you do this, right? Because we already know that we anti-differentiate, and then once we've anti-differentiated, we plug in. And how do you plug in an infinity? Because that means keep plugging in forever, right? And so here's the answer. We're going to write this as the limit as t goes to infinity of the integral of, a to t, right, of f of x dx. So if you end up with an infinite limit, then just substitute a value, a dummy value, hold the spot, and let that variable go to infinity. So we're going to turn improper integrals into infinite limits. That way we can do this part just like we've been doing in all of chapter 7. And then on the very back side of the problem, we're going to have a limit problem to do. And it's been a little while since we've been working on limits, but of course we spent most of fall semester working on limits. So we'll dredge some of that back up and try to remember how to do these kind. This also works. We can call this A if you like. This also works if you go from B all the way in the opposite direction, right? And it works just exactly the way you would expect it to work. This is the limit as t goes to minus infinity of the integral of t to b of f of x dx. Okay, so in terms of integration, there's nothing new here. And really in terms of the whole problem, there's nothing new. You have an antiderivative problem with a limit problem tucked on the end of it. So you want to try one? Oh, I could do one more, I suppose. C. If you have an integral that goes in both directions, from minus infinity to infinity, okay, then what we're going to do is we're going to take the limit as t goes to minus infinity of t to 0. Actually, well, we usually split it at 0, although we could split it anywhere we want, of f of x dx, and add to it the limit as t goes to infinity of 0 to a, I'm sorry, 0 to t of f of x dx. Okay, so this limit is going, or this improper integral is going to exist if both of these exist, and they're going to exist if the limits exist. So let's try a problem. Here's one of my favorites. Where is it? I thought I wrote one down. Oh, I didn't write it. Maybe it's here in the book. See if I can find a nice example. Oh, I like this one. Let's do this one. Okay, so the integral from minus infinity to infinity of 1 over x squared plus 1 dx. How about that one? Okay, so the question is, what is that, right? And if you want to think about what it looks like, you could think about it being an area. And let me get my screen back up there again. You could think of it being an area that looks something like this in Desmos. We would say it's f of x equals 1 over x squared plus 1. You'd say, hey, check it out. That's kind of a cool curve. It looks like it's got sort of a mound-shaped, symmetric sort of feel to it. It looks like something you might see in the statistics class. And we want to know what the area is underneath here if we were to shoot the whole thing. Of course, we could do it with rectangles. If you just put a bunch of rectangles in there, you would get the integral from minus, I wonder if I can do this. I don't know if it knows how to do these or not. Nope, doesn't know how to do those. But we could certainly do this. How about just minus t to t? In other words, how about just some numbers from minus t to t, and then we'll put in some t's as t gets bigger and bigger and bigger. Okay, so if we go from minus 1 to 1, from right here to right here, then the area is 1.57. And check this out. Wow, hey, look at that. What does it look like it's getting closer to?
Pi.
Pi. Looks like it's going to be pi, which is kind of cool. The area underneath here is pi? You mean like the same as the area of a circle of radius 1? Yeah, cool. So how do we do that by hand? We're going to do that something like this. We're going to say, we're going to split this apart into two pieces. Okay, so we have to say the limit as t goes to minus infinity, right, of the integral from t to 0 of 1 over x squared plus 1 dx, plus the limit as t goes to infinity of 0 to t of 1 over x squared plus 1 dx. So notice that we still have to do integrals. Really in chapter 7, doing integrals has been like our primary focus, but mostly doing integrals is part of solving a bigger problem. And so just doing the integral or the integration now is going to be trivial, right? As soon as we finish off chapter 7, or just part of a bigger problem. So here we go. How about the limit as t goes to minus infinity. Remember that you got to keep writing this until you do it, right? So it's a little bit of writing. You guys know any functions whose derivative is 1 over x squared plus 1?
Arctangent.
Arctan.
Yeah, arctan.
All right, arctan from t to 0 plus the limit t goes to infinity. Arctangent. The nice thing about this, of course, when you split it, it's really the same function, so that's pretty nice. Now we got to plug in. So we say the limit t goes to minus infinity. Arctangent of 0, what does that mean? An angle whose tangent is 0. Do you know any of those?
0.
0.
0, yeah, 0. Minus, right, the arctangent of t. Okay, then we got plus the limit as t goes to infinity of arctangent of t, right? Minus 0. Okay, so resolving, let's see. Now all we need to know is what happens to inverse tangent as t goes to minus infinity? Anybody know? This was a minus.
Is tangent an even function?
Is it an even function? Arctan? I don't know. I'd have to put it on the graph, but it's a very good question because then we could combine these and say it's 2 of them, right? Or we could say one's up and one's down and use symmetry. That's a great idea. I'm going to have to look on Desmos to tell. Let me rewrite it first. But notice now that the integration part of this is done, and now we have a limit problem. So what we're really saying is, when t gets really big and really small, what's inverse tangent doing? So think about that. I mean, you could think about it or you could just look, right? We've talked about this before. You can either think first and then look on Desmos and confirm that your thinking is right, or you can just say, oh, it's too stressful to think. I'm just going to look, see what Desmos is telling me. But look at what this is asking. This is saying, I want an angle whose tangent is really, really, really big negative. It might be easier to do this one first. I need an angle whose tangent is giant. So what does tangent look like, right? Maybe you sketch it over here. Here's the tangent going up this way, right? As the angle changes. So we want the tangent to get bigger, 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 bigger. Well, what angle does that look like it's getting closer to?
Pi over 2.
Pi over 2. So I'm kind of thinking like this one over here is going to be pi over 2. How are we doing? Is that making sense? How about this one? Well, you got to say, where's tangent negative? And I think tangent is negative over here, isn't it?
Yeah.
So, but you could also say tangent is negative since it's going down right there. I don't think I want to wander over here to the third quadrant and deal with 3 pi over 2s. Let's just stay right here because, of course, inverse tangent's domain is pi over 2 to minus pi over 2. So tell me what angle would make this a big negative number. And you say?
Negative pi over 2.
Negative pi over 2. And it shouldn't be a big surprise now that you've got a negative pi over 2 and another pi over 2, making 2 pi over 2s, which is what Desmos was trying to estimate for you in the first place. Right?
Well, that's cool.
We could already see it was going to pi. Pretty cool, huh? Now, I really like your idea that maybe we could use some properties of inverse tangent, right, to combine these. In fact, what's happening here? Well, when I go down, this goes down. So when I have a negative angle, I have a negative. So we could have made this a positive and made this a positive and used the symmetry to say, well, this one's just the same as this one, so we really have two of those, right? I don't know if, I only do so good at memorizing things myself, and so I don't memorize all those rules. So it's easier for me to just look on Desmos when I need it, or to just kind of force my way along. But certainly if you were doing a lot of these by hand, you'd memorize the symmetry so that you would be able to kind of shorten your calculation a little bit. I find that I don't have to shorten it too much because I can just pop over here like this, and I can say, well, I wonder what inverse tangent is doing, right? So if I'm looking at inverse tangent, then I'm looking at this green thing. So now I'm feeling like I know what it's doing. I can turn that one off if you like. What's it doing? It's going flat on both sides. So it's going flat over here at pi over 2. It's going flat over here at minus pi over 2. So this has odd symmetry. So if we want to do, so right back in here, the opposite of tangent, right? The opposite of tangent is the tangent of the opposite angle. And then we could change the negatives, right? Are you with me? I don't know if I'd do that. I think I'd do just what we did though. Just look on Desmos and see where it's going. Okay, so what's the feel of these is that we're going to have this improper integral. In other words, we're going to go off to infinity, one direction, the other direction, or both. We're going to write it as a limit problem. We're going to do the antiderivative just like we've been doing all of chapter 7, and then do a limit problem on the end of it. Okay, so these are all pieces that you already know how to do. And so there's nothing new here. It's just all combined all in one place. And of course, it's got some kind of surprising results. I mean, I think it's really cool that the area under that curve turned out to be pi. I mean, that's like, really? That's kind of cool. Okay, so that's type 1. You want me to, we could do one more, but I think I'm just going to keep on going. I think you got the idea. There are times, and I'm feeling really quite happy about our being online and having to slow down our pace a little bit. I'm always really stressed about the fact that we lost chapter 8, and I want to, you know, I feel like we need to squeeze some of that in. Normally, I kind of do this whole section on improper integrals by just saying, oh, it's just a bunch of stuff that you already know how to do all combined in a different way. And then I just go on. And I think that it's really worth spending a little bit more time on this section, because this section is going to lead us into pretty much all of chapter 11. Okay, this is going to be setting the stage for what's happening in chapter 11. And so a little bit more time here, a couple days, maybe it'd be really worth it. All right, let's try type 2. Here's the other type. Where did I make my notes? I have some notes here somewhere. Okay. Type 2. Type 2 are the kind where there's an infinite discontinuity. Okay, and so basically we have a vertical asymptote. So let me put this in here. And we're asking, hey, what's the integral over to the asymptote? So if I put the screen back up here, I'll get this one out of here, get this stuff out of here. And we might consider something that has an asymptote in it, like 1 over x, minus 1, something like that. Okay, so we say, oh man, I'm pretty sure I don't want to find the integral from 0 to 3 of this, right? That's going to be a huge problem. So what happens if I go integral 0 to 3, right, of f of x dx? You're saying I need an f, so I needed to call that f of x. Hello, x. Okay. And it says undefined. Well, that seems kind of like a reasonable thing to say. Look, how do we go across this break? There isn't a function, there isn't a continuous function that's going to work because you can't anti-differentiate, right? You can only differentiate a function that has a derivative, and this doesn't have a derivative at x equals 1. So I'm kind of feeling like maybe going across this break is a bit of a problem. So what we want to do is, first of all, we want to split it up at the break. So if we did this, we'd say, well, what if we did the integral, if I can type, what if we did the integral from 0 over to 1, right, of f of x dx? Could it handle that? Good grief, dx there. Nope, still can't handle that. But I'm kind of thinking we would be feeling a little better if we broke this thing and just dealt with one side, one infinite limit at a time. Okay, so that's going to be our first thing. You have to, and these I think are harder. If it says I'm finding an integral to infinity, it's like screaming at you. I'm an improper integral. I got an infinity in there for the limit, or for the limit of integration. Now this one is a little bit harder because you'd have to say, uh-oh, there's an infinite discontinuity in there. In other words, you have to know there's an asymptote in the middle of this somewhere. So it's not saying go from 0 to 1 and 1 to 3, right? You have to kind of know that on your own. But you can see that from the picture. Okay, so the question then is, well, what do we do? And the answer is we do just exactly what we did before. We do the integral. We could do this in two pieces. We'll go from t over to 3 of f of x dx. And we'll add a slider for t. And then we're going to let t get closer and closer and closer to 1. So I need kind of close to 1. So I'll go 1 to, I don't know, 5. Okay. And if we start over here at 1.5, check it out. We get this area. And then what's happening as I get closer and closer to 1? I mean, how close to 1 do we want to be? Looks like it's getting bigger and bigger. Oops, too many zeros. That looks like it's getting bigger. The question is, does it keep getting bigger and bigger and bigger forever? Or does it, does it get closer and closer to a number? If it gets closer to a number, we call the number the limit, and we call the limit the area, okay, or the answer. If it just gets bigger and bigger and bigger, then we say that it doesn't have an area, or that it's undefined, or that the area is infinite. So here we go, type 2. Whoops. Type 2. Okay, and here's the kind that we want to do. Suppose we have a vertical asymptote at B. Vertical asymptote at x equals b. Okay, then we want to know what's the integral from a to b, right, of f of x dx. And what we're going to say is, hey, that's equal to the limit as t goes to b of a to t f of x dx. Now check it out. We're not going to go to b from both sides at the same time. We're just going to go from one side. And since b is the upper limit, we're going to go from a little smaller than b. So we're going to take the limit to b from the negative side, right, from the smaller side. If we want to go at it from the other side, So this is A, right? Here's B, here's the other limit. Suppose a vertical asymptote at x equals A, then we'd say the integral from A to B, f of x dx, right, is equal to the limit as t goes to, A from the plus side of A to B, I'm sorry, of t to B of f of x dx. And so now we're coming down to A, right, from above. So the question is, do these limits exist or not? This is just the same as the last one. Now you need to anti-differentiate, you need to plug in, and then solve it by techniques from chapter 7, and then add a limit problem onto the end. So here's a nice example. Let's do this one. Here's the example. Find the integral from 2 to 5 of 1 over the square root of x minus 2 dx. So what makes type 2 a little bit harder than type 1 is that there's something going on here, right? That is maybe not jumping out obvious to you. Which is what? What's going on?
Asymptote.
Asymptote, right. Okay, in this section, not gonna be hard to figure out that there's maybe something going on. So if you don't see something going on, then, then I'm kind of thinking that, you're missing something. But in general, you know, you wouldn't know that there's a problem there necessarily, right? You wouldn't expect that there's a problem there necessarily. So check it out, 2 to 5, well, 5's nice, right? 5's nice. But when I go over here by 2, it's getting closer and closer to x equals 2, but it's never touching. So we got a vertical asymptote, right? So there's x equals 2. If we wanted to make it look more like an asymptote, we could maybe make it dotted, something like that. Okay, so we have a vertical asymptote. Notice in this one, we'd even have a bigger problem if we said the integral from, say, 1 to 5. Because over here, when we put in a 1, guess what? There's no function. So there's no antiderivative. So there's no area, right? There's nothing over here. So if I said minus 1 to 5, you'd say, well, that's a little weird. Okay? All right, let's do it. So what do? We say there's something funny going on at 2. And we write this as the limit as t goes to 2 from the plus side of t to 5. So how do you know where to split it and all that kind of good stuff? In the old days, you would have to be really familiar with the domain and range, which is why in all those algebra classes, we kept asking, what's the domain and range over and over and over again. Nowadays, I think it's just easier to look on Desmos and see what's happening. It's easy to see the domain and range when you're looking at the picture. And so look at the picture and figure out what it's doing, and then write it down, and then do it. So here comes the do it part. Remember that when solving limit problems, you have to write down the limit until you actually do the limit. Okay, so please keep writing that down so that I can follow your thinking. And now I got to do this, this integral. So how do I do it? Trig
Isn't it
sub,
just a power rule?
part, power rule, yeah. Isn't it nice when they turn out to be kind of easy? And the answer is yes. But you know what? There's a lot of stuff we could write here for the integral. Okay, it could include all the ones that we can solve using any technique from chapter 7 all the way back through chapter 5, right? But it's just a power rule. So we say it's to the minus 1/2 now. So I'm kind of thinking it must have been to the what? Positive 1/2 before?
Mm-hmm.
I'm going to need a 2 to take care of the half. And so in this one, I think we got it. In the other ones, you might have to pause here a little bit longer because it might take a little longer to solve that integral, right? But once you've got it, then we stick in the 5 and the t. Okay, so 5 goes in. 5 minus 2, 3. So this is what? 2 root 3?
Yep.
And then we get minus whatever we get when we stick in the t. So you've got 2 times the square root of t minus 2. I don't know if it's easier in the square root form or not. You can leave it however it's easiest for you. And now we're saying, okay, what's the limit of a difference? Oh boy, this is like September maybe. You remember this? It's the difference of the limits. And what's the limit of the constant? It's just the constant, isn't it?
Mm-hmm.
Okay, so this is 2 root 3, and this is minus. And what's the limit of a constant times a function? Constant, right? Times the limit of the function. So now I need the limit of the square root of t minus 2 when I go to when t gets closer and closer to 2 from the positive side. So if it's positive side, it's a little bigger than 2. Bigger than 2 minus 2. That sounds like a positive number, which is good because I'm taking the square root. And the square root of a number that's getting closer and closer to 0 is getting closer and closer to what?
0.
0, which means this goes to 2 root 3, bam. And now to check, we got to go back to Desmos and check. And we would say, well, I don't know. What happens when I take the integral from t to 5 of f of x dx when t gets closer and closer to 2, but a little bit bigger than 2, yeah? And you say, well, it looks like that number to me. What if I put another 0 in? Uh-oh, it's getting bigger. It's getting bigger, but the first part of it's not changing. So I'm kind of thinking this is leveling out. And you'd say, where is it leveling out? I'm hoping it's leveling out at 2 square root 3. Yep, those look pretty close. Okay, questions?
Nope.
It's pretty straightforward, isn't it? It's all stuff that we already know how to do. We already know how to find antiderivatives. We know how to evaluate definite integrals, and we know how to find limits. So now you're just putting a whole bunch of things together in one place and sort of getting us ready, building some tools so that we can sort of attack chapter 11. I've got a little tiny bit of a preview from chapter 11. A little preview from chapter 11. And I'm going to do one more problem, then a little preview of chapter 11. We're going to call it good. So here is, here's the challenge, right? So we did a couple, and then I would say, you do one now. So then I would do this, and we'd say, how about the integral of this, right? From, I don't know, 0 to 3. And there's only a couple of things we should really watch out for. What should we watch out for?
There's an asymptote in between the two values.
There's an asymptote in between, right on. So you got to do, just like we just did, 2 pieces, come from the left, come from the right, see what they are and add them up. In other words, we would have to break this up into this problem And this problem and then we would have to realize that there's an asymptote there. So we'd have to write this as a limit as I go to 1 of t, right? And then we'd have to say, there's a limit as I go to 1 from the top side. I'll just put the dx up there. And then you go, these aren't too bad. How do we anti-differentiate these?
It's the natural log.
Those are natural logs. Now plug in the t, now plug in the 0. Don't forget about the natural log of 0. What's the natural log of 0?
Natural log of 0, that's 1.
Oh, close, but no.
No?
I think it's 0, isn't it?
Still no.
1?
No,
Wait, no, it's the natural log of 0. It doesn't exist.
doesn't exist. It goes all the way down. So how can you plug in that 0? You can't plug that in either. So now you're going to check this out. Oh boy, now you're going to have to split it again. So if I say share, and we go over here and we take a look, then really what we got going on here is, so if you put in, why isn't that working? There we go. Natural log of x, right? It's going all the way down here at 0. So what do you get? Minus infinity, right? When you plug in 0.
Oof.
Uh-oh. So maybe we're going to have to go approach 0 from this side. Okay, but I think you've got the idea of how to do this now. There's going to be some paying attention to detail here, but for the most part, not too bad. And I expect that in the problems from this section, especially in WebAssign, the integrals themselves are going to be pretty easy to do. They're not going to be the nastiest ones from chapter 7. But don't be surprised if you don't get some integration by parts or some trig subs, you know, for this part. They aren't all going to be just really straightforward, you know, chain rules. So I'm going to let you finish that one. If you're having trouble, look in the book, right? That one's solved for you in the book. I'm going to let you try to solve it. Okay, so here we go. Last thing. Here is the last thing. And really, this is the beginning, a preview for chapter 11. And I think I'm just going to share the picture from the book because the picture in the book is really nice. Okay. Here's the picture. I think this, and it's easier on the dot cam than it is on the, oops, where am I going? I'm making everybody seasick. Okay, sorry about that. Okay, now check it out. Here's the big idea. So F starts at some value, right, at A. So it's bounded on the left-hand side. And it's going down, going down, going down to an asymptote on the x-axis. G does the same thing, right? It goes up and then down. And it also has got an asymptote on the x-axis. So here's the big question. If F actually goes to a number, in other words, if it converges and the limit exists, what do you think we can say about G? In other words, can G have infinite area if F has finite area?
No.
That doesn't make any sense, does it? F is going to come down and essentially kind of pinch off the area way down there at the asymptote somewhere. Well, if G is always smaller than F, then wouldn't G also have to pinch off the area as well? That's the big idea. It says that if F converges and G is smaller than F, and by smaller, I mean smaller, but yet bigger than 0. If it's positive and smaller, then G has to converge as well.
So in a weird way, this almost sounds like squeeze theorem.
It is the squeeze theorem. You're squeezing G in between F and 0 is exactly what you're doing. And so if F squeezes off to a number, then G has to do the same. In fact, to prove this, we simply use the squeeze theorem. That's it. Because remember how you solve these integrals, you write them as limits. And how do you prove one limit goes somewhere and the other one doesn't go somewhere? Well, we can certainly use the squeeze theorem to prove a limit. This turns out to be a really big idea and really very helpful. Because what we're interested in is this integral. Oops. Oh, I made it so giant now. Here, hang on. Oops, now it's tiny. Okay, about there maybe. We're interested in this integral from minus infinity to infinity. So I would really like to consider the following function, e to the minus x squared. So check out e to the minus x squared. It looks something like this. Anybody ever seen something that looks like that before?
Yeah, it looks an awful lot like that 1 over x squared plus 1.
It does. It looks a lot like the 1 over x squared plus 1, but it turns out that this one is even more special than that one. Notice it's got two symmetry, so I'm just going to double the integral from 0 to t of f of x dx and let t get big. Yeah? In other words, if I can find the area on one side, I can just double it. Okay, so let's see what happens when t, when t gets bigger and bigger. T's pretty big. It's not changing. It was changing back here a little bit in the last few decimals, yeah? So do you think this is going to a number or not?
Yeah.
It sure looks like it's going to a number. In fact, if I add, now you're getting me to, figure out, there we go. Wow, we don't even have to go very far. Oh, we don't even have to go that far. Okay, now, has anybody seen this curve before? And you say, well, it looks like the same curve. All you did was shorten it, right? This is a vertical stretch. So I just squished it a little bit. And what does this do? This is a horizontal stretch. So I squeezed it in and squished it down a little bit. But you guys haven't seen this before, huh? That's interesting. It's not a surprise though. Unless you saw it in high school, our sequence doesn't really help you to see this curve very much. But this is a really famous curve. It's bell-shaped symmetric. In fact, it turns out to be what we call the bell curve. And we use it in statistics a lot. And so it turns out that a lot of things are distributed this way. For example, if we were to consider things that occur naturally, like how tall people are. If we were to go measure how tall people are, you would get a distribution that has this very shape. And so this curve is like the whole entire statistics class. In fact, it's like several statistics classes, and they just deal with this particular curve because in nature, lots of things have this shape. And what we want to know is, what's the area underneath this curve? What do you think it is?
1.
I'm
1.
thinking it's going to be 1, yeah? So check it out. By the time I get to 1,000, this is coming down like an asymptote. And by the time I get way out to 1,000, it's so, we're adding so little area. It's so close to the axis that Desmos is already rounding it off to 1, yeah?
Mine rounds off at 10.
In fact, at 10, it's already rounded off at 1, right? So at 9, maybe you got, whoops, no, 8,
There's
no,
3, I believe.
3. Okay, so at 3, we're almost all the way down, aren't we? It turns out that this area, really important. Okay, like big time important. You can't, there's no statistics. Let's see, you run into this curve in chapter like 4 in the elementary statistics book. So this is coming right at the beginning. Almost all of statistics is going to be involve this in some way. And guess what we want to find? We want to find the area. And guess what? It's kind of a problem, isn't it? Because we would need to take, and whether or not I kind of squeeze it all down so the area turned out to be exactly 1 or not, right? These are just some messy constants that I have to deal with. Essentially what it comes down to is I need to find, right? I'm going to need to find this integral. And if I can find this integral, then I can do it with the stretches in there as well, which means all of statistics opens up to me and life is good. How are we doing so far? I'm getting a thumbs up. Okay, you say, no problem, piece of cake. I can deal with that infinite, in the infinity up here by saying take the limit as t goes to infinity of 0 to t of e to the minus x squared dx. Now I've dealt with the improper integral. And so all I have to do is anti-differentiate this and life is good, yeah? Plug in the t, take the limit, and I'm done with the problem. So what's the big deal? How do I do the antiderivative of that?
Well, I'm thinking it should have something to do with natural log,
Okay, yeah, maybe.
because it's going to be 1 over e to the x squared.
Okay, so I can rewrite it. I'm just going to break it out now because now I'm working just with this, right? I'll put it back in up there later. All right.
The complicated part is it would be a chain rule, but we don't have the derivative sticking around somewhere.
We don't have the extra x. Exactly
So
right.
we could do U sub.
We could do a u sub. I'm assuming you might want to try this.
Yeah.
Okay, du 2x dx. So du, oops, so dx is 1 over 2x du, and x was root u, so 1 over 2 root u du is dx. So substituting, whoops, maybe I'm going to go a little bit smaller. Okay, so we get 1 over e to the u, right? And then dx is 2 root u. So we get 1 over 2 root u du. So it looks to me like we have 2 root u e to the u du. Okay, now what? I mean, yes, we can pull the 2 out. That's easy. Now, but after that, what?
Mm.
Hmm.
Would this be integration by parts?
That's what I would probably try next, because it's looking a lot like a product here, isn't it, in the denominator? So then maybe you'd let this be one part and this be one part and blah, 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 keep going. Here's the bad news. If I do it this way, that's kind of weird. I don't know if I can do that. I just can't see my integration by parts unless I use U and V. So I'm going to do this, right? You deal with it however you deal with it the best. Okay, when I take the derivative of this, what do I get? I get 1 over 2 root x, right? Dx. That looks like it's getting worse. So then maybe you say, well, what if I, switch these around and I let u be the e to the x and dv be the root x. But this root x was in the bottom. Well, it doesn't matter if it's in the bottom or not. When I anti-differentiate this, it's to the half now. It's going to be to the 3/2 power when I anti-differentiate, which means this is going to get messier. So you say, well, repeated integration by parts. Well, then it would just get messier and messier and messier. So I'll let you work out the details, but this doesn't look too promising. Integration by parts isn't going to work. So then what? I'll write a problem back over here since I've messed it up so badly. Okay. So now what? Well, here's the good news. I'm going to maybe cut you off right here because you can keep trying to do the stuff that we've been doing. There's all those techniques from chapter 5 and chapter 7, and we've been learning about them for like 2 months. And guess what? None of them work. In fact, there aren't any techniques that work because the antiderivative of this, okay, the antiderivative of this is not an elementary function. And what that means is that there is no function that we can make out of polynomials or logs or exponents or sines and cosines whose derivative is that. There aren't any. Which means finding an antiderivative for it is going to be really hard using any techniques that we've learned so far. So guess what we do? Come on, you guys know.
New method.
New method, chapter 11. Okay, so we're gonna go on to chapter 11 is what we're gonna do because we can't solve this one by doing anti-differentiation the normal way. Okay, can't be done. In fact, there's a whole bunch of them that are in that category. Let me see if I can find a few more of them for you. Here's a bunch. So if you see these on a test, you have to write, I can't do this yet. They were back in the back. They're in chapter 5. I don't have those notes up anymore. Let's see. Here's, oh yeah, look at these. It turns out that this is not the only function. Check out all these. If you get any of those, okay, then life is going to be not so good for you. In other words, you can't do any of those until we get to chapter 11. And some of them look pretty innocent. I mean, e to the minus x squared, right? Sine x over x, 1 over log x, those seem pretty simple. And yet they don't have antiderivatives that are elementary functions. So when we get to chapter 11, we're going to have to figure out, well, if we've been working for our whole lives pretty much with elementary functions, then what would a non-elementary function look like? And can one of these new things, these non-elementary functions, be the answer to these problems? Right? And that's where we're going. Okay, how do we do these 6 integrals? That's what we want to know. We finish that off, we're done, take the final, go home. Yeah? Sound all right? Okay, so what do we do in the meantime? And in the meantime, we do this. I'm going to switch back over to Desmos. Share screen. How am I doing for time? Okay, I got to wrap pretty quick. Okay, I'm going to switch back over to Desmos, I think. Here I am. I'm going to simplify this again. I wanted to actually put the standard normal curve up there for you, but I'm just going to work with this one first because I think this one's just easier. It's a little taller, right, than the other one because I didn't squish it. And so its area turns out to not be 1, but it turns out to be fixed anyway. And so now the question is, maybe if I go there. Oops. Okay. Notice it has symmetry. So if I can find the area on one side, I'm in good shape. The question is, if we go after this, then is there a way to sort of trap it? And the answer is, I think so. Take a look at this function. Now I'm seeing a little bit of a problem here because 1 over x squared goes all the way up. But if we were interested in just from x equals, say, 1, right, from this green line on, if we were just interested in these 2 areas, then I'm pretty sure that we could say something about them. Would you agree that the area under this black curve is certainly, there is an area in this section right here? I mean, it has one, right? We should be able to find it. Okay. Now take a look at this. What's going on over here? Well, it's coming down. There's maybe some area in here, but we don't know because we can't do the antiderivative. But what about this one? This one's coming down and squeezing as well. But we can do 1 over x squared, right? So if the blue curve converges, meaning that it has a limit and there is an area, then what do you think we could say about this black one?
There's the limit and we can find the area.
You bet, it's got a limit as well. So by the squeeze theorem, right, it's going to also be convergent. This one converges, then this one has to converge, which means there has to be an answer to this problem, even if we can't find it using techniques that we know right now. We call this the comparison test. So we can't find this area yet because we haven't done chapter 11, but we know that this area exists, right? This must exist because the area under the blue curve exists, so the area under the black curve has to also exist. We call it the comparison test. Sometimes it's a lot easier if you're looking for an answer to know that there is an answer. Okay, so we call this existence. And so the very first thing that you might want to do if you're saying, I wonder what the area is to ask yourself, well, does it even have one? Because if you go hunting for an area that doesn't exist, then that could be annoying at best. right? So if we know it has an area, then we should be able to keep rooting around, right, until we actually find a way to determine what it is. And that's what we're going to be doing in chapter 11. Okay, so that's a little preview of where we're heading, right? We're going to, and a chance for you to sort of use some of your skills that you've been developing here in chapter 7 to do something new, right? Use your integration skills to find some improper integrals, and then start getting your head wrapped around finding some limits again, because that's what calculus is all about. And that's how we started this class way back in August. And guess what? That's how we're going to end this class in chapter 11, is by taking a look at limits once again. Okay, so I think that's it for chapter 7. I'm going to let you guys think about it for a couple of days, you know, finish off the problems, and then you can ask me questions if you have some. And then next week, right, I would like to do the chapter 7 test. Okay, and we can, I don't think, you know, you could tell me, well, let's not do it. Let's do a shoot for Wednesday. Okay. And what I might do for you, I haven't decided yet. The powers that be at the college would like some form of proctoring going on. So what they would really like for me to do is see you doing your test. In other words, you come on to a Zoom meeting and then you just, you know, put your camera on like you have right now. And then I watch you take the test, right? So that we can say, yes, it was their work, and we can, you know, verify that there wasn't any outside sources and all that kind of good stuff. And I'm not that worried about it, about chapter 7. I mean, at this point in your careers, you either want to learn this and need to, you know, and so I'm kind of thinking that, you know, you've got some pride and such that, you know, you're not going to be off doing things you shouldn't be doing. So for chapter 7, what I'm likely to do is do the same thing I did with the quiz, is just give it to you, get it back. Okay. But to be able to have some sort of, you know, to be able to answer to my bosses that I'm doing some kind of test, you know, supervision, I think what I'll do is we'll have a fixed window. So you'll have to do it during class time, right? Whether you want to be on or not, I don't know. But what I'll do is I'll make it an assignment in Canvas. I'm going to open it at, you know, 8:30 in the morning when we usually have class start. And then I'm going to close it at 10:30, you know, and, you know, give you a little extra time, 2 hours or something like that. Okay. So it'll just be open for a window. So you'll have to sit down and do it. And then I can say, yep, well, we had it timed and I proctored it and, you know, it's all good. Does that sound like a possibility?
Would it have to be submitted on Canvas within that window?
Yeah, well, yeah, but, you know, if that was a problem, I could work with you, because I would certainly be here, sitting here, you know, and so if you had some trouble just getting it submitted, then yeah, we could give you some extra time, but maybe we make it 3 hours, okay? But I don't want it to be a time issue for you, but I would like to be able to say, hey, it wasn't just a free-for-all take-home. We actually, you know, sort of proctored this as best we could using our online environment. And I think that would make my bosses feel a little bit happier about things. Does that sound reasonable? Okay. Let's shoot for Wednesday of next week for that. And that way, if we have some folks that come back, you know, on Monday, sort of the official time that you're due back, we can kind of get them up to speed and tell them what's going on, and we'll figure out how to deal with it. But I don't want to, we can't just stop and do nothing until next Wednesday. So when you guys come back this Wednesday, right, I would like to take a look at section 11.1 and get moving down the road, because there's 12 sections of chapter 11 and we have 15 days left. And we might need to, you know, maybe spend 2 days on one section somewhere down the road. We might also not do every section of chapter 11. but I'm thinking we have to do most of chapter 11. It makes up a big, a big part of this class. And so I'd like to get started as soon as we can, maybe when you guys come back on Wednesday. Okay, that's the plan. Questions, comments, concerns? No, good luck. Some head shaking. No. All right. Well, if you guys have problems, you're welcome to come back during office hours. You're also welcome to send me an email anytime, and I will do my best to get back to you. And if you're doing okay, then I will see you on Wednesday.
Sure.
All right. See you then.
Okay.
All right.
Have a great
Yeah.
afternoon.
You too.